your beta true cut the eigenvector. Of course, once, yeah. The beta PCA is what I'm telling you that everybody's doing when study P functions and you're done. When you study y as a function of x, it's more difficult because you study y as a function of x, it's more difficult because you pass from calculus 1 to calculus 2, okay? Because it's y as a function of several variables. And therefore, somebody found that you can study this regression and then go to the one that you want to study. And then our model, we're saying, okay, how x depends on y? Depends through y through this matrix that is P by D. Okay? When you have this thing, PLS for y given x is true when the model is linear, okay? And they say, okay, we are under the PLS model, x depends on y on this way, this is a matrix P by D. Okay, it means that y depends on x only of this linear combination, and the PLS model is true if it's linear. And they say the following: if I compute the covariance of x here, believe me, is this product of this matrix time plus a constant time identity. Okay, this is the covariance of x under this model. And they were, to prove that it's not consistent, they were asking that theta to be orthogonal. Okay, this doesn't matter because it's you can put everything here. But they were asking that the norm of the columns has to be bounded. Okay? What is the meaning of this? Suppose we are thinking that P grows. P grows means that this has every time more and more components. And this theta is going to grow like this because suppose this 1 is P by 1. And I'm saying I am adding x, but this has a final norm, a bounded norm. What I'm saying that when I added x, I'm not adding information about y because I'm telling you this has to be bounded. Okay? This is, they ask the condition that this has to be bounded norm. That is the meaning. I try to convince you that it means that if you're adding x, you're not adding more information because this has to be bounded. And therefore means this has to be bounded. But when you look data, I will show you a real data. When you have this data, doesn't have to be true. And I want to convince you, if you have data that is a curve, and I'm telling you, I consider this discretization, okay? It's only a few points. What they were saying is, if you take the points in the middle, they are not going to add information. In my x, if I discretize x in 10 places, and give me some information about y, and this is a curve, if I'm adding the points in the middle, it's a continuous function. They have to give information about y. It cannot be that the first point we're given information and this point don't give information. And this is why, and I will show you an example, that it doesn't make sense that this has to be bounded. Okay, in fact, what they were asking, when they were asking this to be bounded, they were asking that is a sparse in the sense that I'm adding x that is noise and doesn't have information about y. This is a conclusion that the hypothesis that they were putting to have inconsistency effectively impose sparsity to get the non-consistency. This was one of the first paper that we did about this. We consider, again, this is a more general model, but under the same model that they were considering, what we were getting was this one. This is consistency. This is for the new x, and I'm seeing the difference between the beta and the beta hat. If I see this number, this is an order, it means what is the order of this difference. If we look at our result says this is the order of conversions. Of course, if this is bounded, you don't have this thing here. You are going to have consistency only when P over N goes to 0. But if you are adding information, if this is giving the new x are giving more information, this is, suppose the information is P to the alpha, meaning that P to the alpha predictors are giving information about y, I have this order of conversions of, if every predictor gives one that we call abundant regression, we have the traditional square root of inconsistency because this one cancel out with this big P. Okay? Well, now, of course, we have emotional result, etc. Not only this one, and the consistency of the prediction and radio conversion depend more or less of the radio between the garbage that we put with the new x, mean error, and the information that we are adding with the new x. That is the difference between sparsity and abundance. I want to show you why I'm saying that they work with abundance regression. And this is our data from these people in chemometrics, and they have this following. They have only n 50, n is equal 50, and they have 101 predictors, meaning n is much less than p. And then they reserve 57 samples that they know the y, but they reserve to see how good is the method, okay? They always do that. This is we take from them is they consider that they need they need 4 linear combination, and the model is true and the 4 linear combination. And what we did is the following. We consider this 101 predictor, and first we took only few of them, 10 of them, AQ space, because this was not in time, but suppose it was like in time. We did the beta hat PLS, and then for the test data, we compute the error. Then we consider a more fine discretization when we took 20 predictors and we did the same. And we compute the error for the new data. When we consider P equal, look at this, when we consider P equal 10, mean we consider only 10 of the predictors, and not the first 10. We consider 10 EQ space predictor, we did the beta PLS, the estimator, we compute the error in the new data set, and the error that we got is here. As soon as we increment the number of P, the error was decreasing. Again, this is in the new data, in the data that we didn't use to compute the beta hat. This is very clear. Here is the rate of conversions is very quickly, and I think it's because you can see here, as soon as you put more predictor, the predictor are giving information about y, and I'm getting better error. If you do here Spark PLS, you don't get this, because when you do Spark PLS, you are going to look for only a few P, and you are going to get something more here than there. Of course, the thing is, as a statistician, when we did this paper about the consistency, when we proved this about consistency, this is an awful computation because there is not too much things to be done in this context. There are no techniques to do this, and then we did like brute force. But usually, statistician, the consistency is okay because it's telling you that the predictions are okay, but usually what we want are confidence interval. Why? Because you want to see that your estimator not only goes to where it has to go, but you want to see how, what is the error. Because of that, usually what we want to have is what we call in statistics a confidence interval. Confidence interval is this is the usual thing that you study in the first class of statistics. Is we do a confidence interval because we have results. Okay, the confidence interval that they are these type of things for the usual thing you get because you prove that not only this is going to this one, but when you multiply by the square root of n, it's like a normal. That means that this means a lot of things, like the rate of convergence is like a square root of n, and you can do the confidence interval because in some way this is the error. Of course, this is not an easy task here, and if P was fixed, we know that PLS and n goes to infinity. We have the asymptotic result for saying what are the confidence interval. Where this P now is a complicated thing, it doesn't matter. What we could prove first that a result like this was true. Let me see if I have here. Okay, when we prove here in 2022, this is for t equal 1, it was very complicated. It's not very complicated, it's not a nice way to prove the result. We would like to have better proof, but well, it's what we got. Here is the square root, this seems to be missing. We got the result of asymptotic normality, and then we can do, this is asymptotic normality is when P and N grows. And of course, under some conditions, and now we are finishing the paper for d equal greater than 1 about a confidence interval that is going to allow us to do not only the prediction, but to do how confident we are about our result. Okay, I think it's enough. It's half an hour, but we are going to say so. This is the one that I wanted to show you that they have this is the one that I want to show you that they have abundance regression, that they were not under. I told you that somebody proved that they no consistency. Yeah. The thing is, I wanted to show you that they were in the hypothesis that they were put in there. It was like the covariance of sigma was bounded. What I want to show with this, bounded means that if you add predictors, you are not adding information. This is a real data set where I show you if I use only P of them, the error is going to be much bigger than if I get a bigger P. ¿Cuál es? No.
The data PLS, they used it for 30 years. It worked, but they didn't have any idea why it didn't work.
This is why when we published the first paper, they invited us to write a paper in their journal, like a cover paper. They didn't care too much, they didn't understand too much, but they want us to say the methodology.
It works. It's consistent.
Yes. It's not that they care, but they were criticizing them a lot to use that method. Okay. This is why.
Okay, you have another question there.
I brought the edition.
I have.
Yes.
Thank you. Liliana brought me for questions, if any. If no one had questions, she invited me for them. No, very nice talk. Thank you very much. I have two questions here. One is in the set of the thermometrics, in the set that you do have curves. So why do you discretize curves and you do not look at the curves as curves? I had a student, we wrote a paper on this, and then you don't, because you do not have 101 observations, you can fit a curve with maybe 5 parameters. We use it splines, but you can use whatever you want. And now you have much less, and you all have all the information. So this is one question is, I do not know why the people from chemistry do not want to look at this, because it's a much more natural way of looking, because you do have curves and you should look at the curves. The second one is, I do not yet exactly, I'm not a specialist on partial least squares, is what is the size of beta hat PLS?
It's P.
Is P?
But it's like PCA, where you project and you consider, instead of X, you project X in D components and you do the beta. It's like you do the beta hat like you are. Okay, in PCA, what do? You have an X, you project, now you have D component and you do OLS, okay? Here is the same, but the projection is going to be the PLS projection.
Okay.
I mean, it's PCA, but with a different projection.
Okay. My question then goes like this. In PCA, my problem with PCA is that you do not have the original variables, and then interpretation is very hard, because you say, okay, I have 5 oranges, 10 apples, and 11 pears, and now I do a combination of this, and my new variable is a combination, it's just like a fruit vitamin. And when you go back, you do not know the effect of each of the variables in your regression. Do you have the same problem here?
Okay. Well, I think you answered with the first question. It's true that the beta PLS you can consider like curves, but the results, for example, Peter Hall proved the consistencies of PLS for curves, but the hypotheses are very, I don't know how to say, it doesn't, I mean, the hypothesis that he put to have the consistencies are not like abundance or something like that. They are like very, I don't know how to say, it's not easy to see if you have that in the data. But I will tell you, I always thought, and I was trying to get the result and I couldn't, to see how these two results match. In the sense, the curves, this is a friend of mine is always telling me that we should do this with the curve. It's true. I agree with you, but you prove whatever you can prove, no? I mean, in the sense that, but I think there is a connection between the two things for sure. I mean, I think this is true because they are curves, and you have the same. The other thing is, okay, if you do curve, you have a beta that is a curve, no? Your beta hat is a curve. Here is the same. You can consider that you project, or you can consider you have beta transpose X, and your beta is the one of the interpretation. But here for PLS, I think in the econometrics people, I don't think that you want an interpretation of each variable. This is why you don't use a sparse PLS, because I think the whole curve is telling you something. And to say, okay, the interpretation of each component, I don't know if it makes sense, but I don't know. But the curves, I agree with you. Totally. But I think it should be, I was trying with a friend that is a numerical analyst to try to see the connection, why one result with the other result. But I couldn't. Because I thought the result for Peter Hall should be important because he proved the consistency, but then he has so many conditions that, but it's an open problem, I mean. It should be nice, because these are very nasty computations.
Okay, any other question or comment? Well, thank you, Viviana.
We can continue, yeah. We are shifted. Yeah. We are 20 minutes.
No,
sí, mira, sí, mejor, ¿no? Sí, mejor. 2 minutos.
Somos todos los que están.
Ok.
¿Cuántos? Sí, antes no había cortado nada, porque sí, ahora sí está
bien, nosotros seguimos. Seguimos y salimos antes.
Eso, no había cortes antes.
No, es que estamos adelantados.
Tem um banheiro aqui pertinho, sabe?
Está bien. No, pero es porque creo que, bueno, nuestro speaker necesita 6 minutos. Ahora bueno.
Teve uma troca aí falar, não? Quem é esse? Só, né? É um banheiro. Ainda bem que está estou trocando o piso lá. Não, ontem eu não podia entrar.
Na sua sala?
É, porque quando eles estão colando, você não pode pisar.
Ah, é.
Enquanto estão tirando, não, mas na hora da colagem. Veja.
Vou tirar férias. Por enquanto, fazendo na minha porta, eu vou tirar férias.
Não, mas eu acho que o seu é o segundo, né?
É.
Daqui a acho que uns 15 dias já chegou. Ah, você está entregando agora? Você vai agora no meio do semestre e já passa a bola, né?
Não, mas eu só entregar um curso, né?
Não, eu sei. Mas aí, bom, aí você vai. Mas é 2 dias só, 2 dias de interrupção.
Sao Paulo, Brazil, and he studied a PhD in mathematics and impact, and he was a Paulson postdoctoral fellow at IMPA also, and the Weizmann Institute of Science, and after in the University of Maryland, and he has a Sophie German postdoctoral fellow at University Paris Sud. And now she held a position at Universidad Federal de Ceará. I don't know, he was in Será, in Fortaleza, and now he held the position in Sao Paulo. And thank you to be here, and welcome. Thank you.
Hello. Okay, do you hear me well? Yep. Okay, so actually, thank you for the organizing committee of bringing us together here, in particular to Jacques, who invited me in person to come in here, and it's a great pleasure to to give this talk. I know it's a little late, so I'll try as much as I can to attract the attention of you, and not going too technical in the calculations that the paper is about. So the title of my talk is Measures of Maximal Entropy for Discussing Billiards, and I expect that at the end of the talk you know all of the words that are in the title of the talk. And the main result is actually joint work, I should say this before I forget, with Davi Obata, who is now is a Brazilian working now at Brigham Young University, and Maurício Poletti, who is a Paraguayan working now at Universidade Federal de Ceará, where I was until last February. So let me start with the beginning, which is to say what a billiard is, a dispersing billiard is. So I'm going to consider the two toros, which we all know with the proper identifications, and inside the two toros I'm going to consider a finite number of convex sets and pairwise disjoint, such that OI intersection OJ is empty. Okay? These I'm going to call them the obstacles. So for instance, a very is when you consider only two obstacles, both of them equal to disks. One of them I'm going to locate in the center of this fundamental domain, so this is a disk, and the other one I'm going to locate at the vertex of the fundamental domain, so due to the identifications we see like this. Okay? So these work as obstacles, and what I'm interested in is in seeing the behavior of a point particle in the complement of the obstacles if you leave it walking at unit speed in straight line. So what happens if you start here, for instance, with some direction at unit speed? It goes, and then it hits the boundary of one of the obstacles. And whenever it hits the boundary of one of the obstacles, I'm going to assume that it suffers a specular reflection, so the angle of incidence with respect to the normal here is equal to the angle of reflection. And then it gets a new direction that it continues to walk at unit speed until it again hits another boundary of another obstacle, and it gets reflected with the same law, and so on. Here we have an identification, so it goes down, and then it continues like this, and it gets reflected, and so on. Okay? So this gives rise to a dynamical system which is usually called a dynamical, a billiard flow. It is a flow, so for each position and direction, at time 0 you can associate the position and direction after time t, so it's naturally a flow. But for us mathematicians, and especially dynamicists, when we want to understand the properties of this flow, it is easier for us instead to understand the properties of a map. And what is the map? The map is just a collection of all positions and angles that you are hitting the obstacles. So if you know here this position and the angle that you hit the obstacle for the last time, you are able to see what will be the next position and angle that you will be hitting the obstacle in time 1 and then in time 2 and so on. So actually we consider here a map, and this map is defined in a space M, so I'm going to call this the billiard map. And the space, the phase space is what? Is the space of all possible positions in the boundary of the obstacles, so it's the boundary of the union, so the union of the boundaries of OI times all possible angles that you make with the normal at this position, so it's just an interval of possible angles which is minus pi over 2, pi over 2. Okay? So basically each of these components is the boundary of OI, something like a circle, and then you make a Cartesian product with minus pi over 2, pi over 2. So since the guys are disjoint, this is a disjoint union of some cylinders. So the phase space is very simple. But the dynamics is quite complicated. So the dynamics, as I already told you, you associate some position r and some angle phi with the next position r tilde and the next angle phi tilde. So the map F sends r theta, a position and angle, to the next position that you hit the obstacles with the next angle that you are hitting. Okay? And I assumed that these guys are convex. So since they are convex, this is exactly an instance of a specific class of billiards which are known as dispersing billiards. And why do you see dispersion occurring here? Well, if you recall the laws of optics when you see in school, if you have some mirror which is like concave from here, if you have a beam of light, right, parallel arrays of light that are coming, when they hit the mirror, they get reflected and they get dispersed. Correct? So that's why these guys are called dispersing billiards. And this dispersion effect is actually the first instance that tells us that for some reason these billiards, they exhibit a very big chaotic behavior. Because even though you have two initial conditions that are very close together, after a single hitting in the obstacle, it already gets dispersed. And in the next iteration, it gets even more dispersed and so on. So you have a very strong sensitivity to initial conditions. Which is exactly one of the ways that people in dynamical system like to quote the term chaos. Okay? So the idea of this talk is in some sense to try to understand this chaoticity of these dispersing billiards in some way. But this started a long time ago, and this class of billiards was actually introduced by Yakov Sinai in the late 60s, around 67. He developed a very deep theory of these dispersing billiards, and his first instance was actually to try to find some invariant distribution of points for which this map here makes the measure invariant. So what do I mean? He actually found a very specific probability measure. So if you get dr d theta, this is the Lebesgue measure. The Lebesgue measure is not going to be invariant, but if you put a cosine here, then this is going to be a measure which by definition is equivalent to the Lebesgue measure, and this one is an invariant measure. If you wanted a probability measure, so you just divide it by 2 times the length of the boundary. Okay, so Sinai found, and I think that he was actually motivated by the laws of physics, because related, as I told you, to this map, there is this billiard flow. And the billiard flow is like a mechanical dynamical system. And because of the laws of mechanics, he was able actually to cook up this measure which is invariant under this map F. Just to recall to you what invariance means, it means that if you look at the phase space and you have a set A, if you iterate, here I can iterate it forward because the map is invertible. You have f of A, and saying that this measure is invariant says that mu of A is equal to mu of f of A for any subset A, Borel for instance. Okay? So it's like an invariant distribution. And Sinai was actually able to prove many interesting properties of this measure. For instance, he was able to prove that this measure is what we call ergodic. Ergodic means that you cannot decompose this measure into 2 other invariant measures. So from the point of view of invariant measures,
¿Qué? ¿O te vas? A las 8 de vuelta a Our next speaker is Nasser Salti of the National University of Science and Technology in Muscat, Oman. And he was a
He was a young affiliate of TUAS and TIAN, the young part of TUAS, between 2017 to 2021, and he's interested in the following areas in applied math, in, I don't know, physics, magnetic reconnection, nanofluids, dynamic fluids, a lot of physics, differential equations, and biology. Thank you so much to be here, biology. Thank you so much to be here. We are very happy.
Thank you very much for the introduction. Thank you very much for the introduction. Thank you for the organizing committee. Thank you for Prof. Jacqueline for the invitation. Organizing committee. Thank you for Prof. Jacqueline for the invitation. It's very nice to be with you in this celebration. Nice to be with you in this celebration of 30 years of UMALCA. I'm trying to be more focused because the biological time now is more focused because the biological time now is already exceeding midnight. This is 7 hours exceeding midnight. This is 7 hour difference. So if I said anything that does not make sense, please excuse me. Okay? My talk is about mathematics. Okay? My talk is about mathematical analysis of a Zika model with reservoir and human movement. This talk is a joint work with other colleagues from Sultan Qaboos University in Oman, namely Professor Ibrahim al-Mujtama, Fatma al-Musalhi, and our PhD student, Kifah. We are interested to see the effect of human movement and non-human reservoir in the transmission dynamics of Zika, and our dynamics of Zika. And our talk will be a brief introduction, and then I'll just go and explore our previous models without any non-human primates, and then we go to our main problem, which is a model with non-human primate. And we'll talk about 2 submodels of that one, and then we'll go through a complete mathematical analysis without any going to the calculations. We'll just try to give the idea of what's happening in there for both these 2 models. Zika was identified in 1947 in Uganda, and then in 1954 it was reported that in humans for the first time in Nigeria. And then outside Africa and Asia was discovered in 2007 in the island of Yar, and then it becomes a real issue of public concern in around 2016, and was including, I think, Brazil, and there are largest epidemic took place in 2013, 2014, and also a big one in India as well. To model any epidemic disease, it's very crucial and important to know the transmission routes. In Zika, the main transmission route is through the bites of mosquitoes, but also there is a direct human-to-human transmission, and also there is also what we call it vertical transmission from a mother to her child during pregnancy. Symptoms is fine, it's just mild symptoms in there. And these symptoms usually duration within 2 to 7 days after the bite. And motivation, of course, as we have seen in many epidemic diseases, mathematical modeling play a major role in understanding the transmission dynamics, given idea the management of such diseases. A number of mathematical models there, diseases. A number of mathematical models there for Zika, but